Hello, in this section I want to point out a problem with generative models such as naive Bayes models, which is how they can overcount evidence when it's correlated, and at least hint at how Maxent models can solve this problem. I'm going to use this example. So in this example, here's our training data, and in our training data we have 8 documents. And so 4 of those documents are about Europe, and 4 of those documents are in the class Asia. And we're wanting to do a 2-class classification problem between documents about Europe and Asia. Now to keep this example small, I'm building a text classifier with a very teeny vocabulary. You can always truncate the vocabulary used in a naive Bayes text classifier, and people often do to make the models smaller, more compact. And in this example I've done that to an extreme extent, and so I only have 3 words left in my vocabulary. And so in the documents, we're just looking at instances of those words. So in the first document, there's 2 instances of Monaco and no instances of the other 2 words in my vocabulary, which are Hong and Kong. Okay, so if we look at the overall statistics, what are we starting to find? So we've got 4 documents from each class, and there are 8 documents in total. So the prior probabilities of Asia and Europe are half each. In total in Europe there are 8 words and 6 of them are Monaco, so the probability of a word being Monaco, given that it's in the Europe category, is 3/4, 6/8. Okay, looking at the Asia category, there are again 8 words in our training data and 2 of those are Monaco. So the probability of a word being Monaco in the Asia category is 1/4. Now let's suppose we've now built our naive Bayes model and we're going to classify a document. So here's our picture of the naive Bayes model, and for this particular document the only word from our vocabulary that appears in it is Monaco, that appears once. So what does our model predict? So for the joint probability of Asia and Monaco, we've got the prior probability of Asia, that's a half, times the probability of Monaco given Asia, which is 1/4. Then the joint probability of Europe and Monaco is the prior probability a half times 3/4. And so to work out the posterior probabilities, we're going to take each of these terms divided by the sum of the 2 to normalize it. And so what we have here is 1/8 and 3/8, which is going to give us 1/4. And for Europe we're going to take 3/8 over 3/8 plus 1/8, which simplifies down to 3/4. So this isn't surprising. This gives us exactly what we'd expect. So what we saw in our training data, there's Monaco appeared 6 times over here and twice over here. The 2 classes are equally likely. So if we've got a document with just the word Monaco appearing in it, well, we expect to say there's a 3/4 chance it's a document about Europe. That's a naive Bayes model working correctly. But now let's look at another example. In this example, we have exactly the same training data, so the prior probabilities of each class is a half, but this time we're going to be working with documents with Hong and Kong in them. So the probability of a word being Hong, given it's about Asia, so that's 3 out of 8. And the probability of Kong being it's about Asia is again 3 out of 8. So that's 3/8. Then over here for Europe, there's 1 instance each of Hong and Kong, and there are 8 words in total, so we've got probabilities of 1/8. Okay, now let's again move to test time. So here's our naive Bayes model, and our document that we're testing on has the words Hong and Kong appearing once each and nothing else from our vocabulary. Okay, so if we work out the same kinds of probabilities as before, we get a half times 3/8 times 3/8, and here we get a half times 1/8 times 1/8. The denominators are always the same, so we can just look at the numerators for working it out. So this is proportional to 9, and this is proportional to 1. So then when we work out these posterior probabilities, for Asia we get 9 over 9 plus 1 equals 9/10, and for Europe we get 1 over 9 plus 1 equals 1/10. So look at what's happened. The classifier is now giving 90% probability that it's an Asia document rather than just 3/4. And intuitively that doesn't make sense, that the answer should be exactly the same as from the document with just Monaco. Because look, Hong Kong appeared once in a Europe document and it occurred 3 times in Asia documents. So the probability should be 3/4. But why did that not happen? Well, that didn't happen because although I'm suggesting now that Hong Kong is one word, the name of one place, in our model it's being treated as 2 completely independent words that have nothing to do with each other. And so it counts the evidence for each one separately, and so that's precisely where you're getting these 3/8 times 3/8 and 1/8 times 1/8, and that ends up with you having this odds ratio of 9 to 1 in favor of Asia, whereas previously when you had the document with just Monaco you had a ratio of 3 to 1. So you're sort of multiplying in an odds factor of 3 for each repeated instance of the word. So what's going on here is that really we have one piece of evidence, appearance of the word, the place name Hong Kong, but because it's 2 tokens, we're treating it as 2 separate pieces of evidence, and so we double count that evidence, and we're falsely confident that the document is about Asia. Does that create problems for classification? It turns out it does. Let's look at one more example. So in this example, everything in the naive Bayes factors is just the same as before. We have exactly the same training data that we're building a model from. But this time, at test time, we've got exactly the same naive Bayes model, but our document of interest has Hong Kong, Monaco, 1 time each. So what does that mean we get when we work through our naive Bayes model predictions? So if the joint probability of Asia and all the words is 1/2 times Hong given Asia 3/8 times 3/8 for Kong times 1/4 for Monaco, the probability of this joint probability is 1/2 times 1/8 times 1/8 times 3/4. Again, the denominators are the same and can be ignored, so the posterior probability of Asia is then going to be 3 times 3, 9 over 9 plus 3. So that's then 3/4. And the posterior probability of Europe is going to be 3 over 9 plus 3 equals 1/4. And so look at this. What we've gotten out is that there's a 75% chance that this document here is an Asia document. And intuitively that doesn't make sense. Informally, in the training data, there are 2 documents that look just like this, and one was about Europe and one was about Asia. But more precisely, we have these statistics that the place Monaco appears 3/4 of the time in Europe documents and 1/4 of the time here, and the place Hong Kong occurs 3/4 of the time here and 1/4 of the time about Europe. So those 2 factors should just completely cancel each other out, and we should say that this document is equally likely to be a document about Europe or Asia. But again, we don't get that effect because the 2 tokens here are wrongly being treated as independent sources of evidence, and so therefore we think we still have a 3 to 1 odds ratio in favor of the document being about Asia. Okay, so what we've seen is that naive Bayes models will multi-count evidence that when it treats evidence as independent, even when it's partly or totally correlated with other pieces of evidence. Each time you see a feature, it's being multiplied in. And what we're going to show in the upcoming part is that maximum entropy models pretty much solve this problem. They completely solve it when two pieces of evidence are completely correlated. And as we shall see, this is done by weighting features by a more complex algorithm that ends up meaning that the model expectations of features match their observed empirical expectations. Now, obviously there are names of places like Hong Kong or Saudi Arabia that are provide two tokens that are very correlated, but you might still be thinking that this doesn't come up very much. But the truth is that when you're building feature-rich classifiers, defining features as we discussed before, this happens a ton. Let me just quickly give you one more example. So suppose we're doing some medical documents, and a word we might have in the document collection is Xanax, and we'll have that as a word feature. But we discussed how commonly you also want to have substring features and for prefixes and suffixes. And so that means we might have a feature for the first four letters of a word as Xana with a capital X, the first three letters of word are Xan, and the first two letters and the first letter. But the problem is, it's quite likely in our training data that the only word that we ever see that starts with capital XAN is Xanax. It's a very rare beginning of words. And therefore, this feature will fire only when the word is Xanax, and this feature will fire only when the word is Xanax. And so these three features, their occurrence will be completely correlated with each other. And so if we build a naive Bayes model with these three features, we'll triple count one piece, what's really one piece of evidence, whereas the maximum entropy model won't do that. Okay, I hope that's given you a sense of the problem and motivated you to stick with the math that comes up ahead in explaining how maximum entropy models work.